Swayam Prabha. Digital India. Educated India.
Welcome to the fourth lecture of this series on surface engineering. We are still discussing the fundamentals of solids before we enter into the elaborate discussion on various kinds of surface properties and processes that are considered as surface engineering. In the last lecture, we talked about defects in crystals. So what we realized that dimensionally one can have various kinds of defects. In this particular lecture, we are going to talk or essentially discuss the reason why surfaces arise, the genesis of surface energy, and how does surface energy or various structures and properties of surface affect the overall performance of any solid. In fact, the whole course is on surface engineering, so we must understand what do we mean by surface. Now, surface essentially is an entity where the continuity of the aggregate breaks down or ends. Now, if you imagine a set of atoms which either are manifesting in the form of crystals or crystalline aggregate where we have three-dimensional periodicity, or if you can have a situation where you do not have three-dimensional periodicity. So, be it crystalline or amorphous, in either cases we will have a situation where a certain continuity gets broken down or ends at a particular site. So, wherever such continuity ends, we create a surface. So, for that matter, if you take any solid, you can always imagine that the solid, no matter what you have inside, certainly has an outer contour, and that is where it actually interfaces with the surrounding or with the atmosphere. So, we can have such a surface, we can have such a situation where the continuity breaks down onto the external surface. But such surfaces can exist even inside the solid, which we don't get to see by naked eye because the solid in all probability is an opaque solid. But if it's a transparent solid, you may actually discover that there are interfaces within. So, in general, let's say surface is essentially a situation where the atomic or ionic or molecular aggregate ends its continuity, and this kind of situation where the continuity breaks down can happen either at the external surface, which is the solid vapor interface, or within the boundary, within the bulk of the solid, and which we call internal boundary. So, the boundary is essentially either vapor solid or solid liquid or solid solid are all qualified to be called as external or internal boundaries. In fact, you can have for a situation where the two vapor phases are immiscible, or if we have a situation where two liquids are immiscible, there also you can have interfaces. But since we are talking about solid surfaces here, so we essentially should concentrate on solid vapor interfaces, which is the external interface, or solid liquid interface, which also could be an external interface in a situation, for example, when a solid is growing out of a liquid, or in most of the other cases we have solid solid interfaces which are called internal boundaries. So, boundaries, surfaces or interfaces, they essentially allude to the fact that there is a discontinuity of periodicity, there is likelihood of having certain density of defects. We certainly have broken bonds because we do not maintain the same surrounding as we can have inside or in the interior of the crystal. And as a result of these broken bonds, we certainly can imagine that there should be existence of an energy component which is different than that of inside the bulk. Now, talking about the solid-solid interfaces, which is what is very, very important for defining all the properties of solids that we see, they can be of two types, either the so-called homophase or grain boundary, or heterophase or phase boundary. What it means is that if the entities across a particular boundary are having the same crystal structure and same composition, only differing in orientation, then we simply call it grain boundary or homophase boundary. On the other hand, if you have a situation where the two entities across the boundary differ in crystal structure, differ in composition, then we call it a phase boundary or interface or heterophase boundary. Now, all the boundaries, whether it's a grain or phase boundary, they can be characterized in terms of their structure. Boundaries also do have their own structure and primarily containing certain amount of defects. The boundaries are characterized by misorientation or the angle of misorientation between the two crystallites, and certainly in terms of the energy they carry. So, as taking cue from these kind of basis for differentiation or classification, we can have high angle and low angle boundary, where usually the angle of misorientation is below. When it is below a few degrees, we call it low angle. When it is several degrees, then we call it high angle boundaries. And these boundaries actually can be either the tilt boundaries, and that's where you actually can easily explain the explain the misorientation angles. You can also characterize the boundaries in terms of energy, and you can also explain in terms of the coherency or the structural match across the boundary, and call them coherent, semi-coherent or incoherent boundaries. Now, as I said, that surface is the position where the continuity breaks down, and as the continuity breaks down, so if you consider an atom sitting in the middle of a crystal and an atom located onto the surface, then the surface atom certainly will enjoy at least one extra degree of freedom, which means that the atom in the center will be pushed and pulled by all the atoms surrounding it. That means it's pushed and pulled from all sides, whereas the one at the surface will have such attractions or repulsions from all around except from the top or the bottom. And as a result, there will be certain bonds which are not matched by the counterparts from the top or the bottom, and hence these broken bonds will actually, the cumulative effect of them will actually be manifested in the form of what is known as surface energy. If you just compare two possible situations, that when you allow a drop of ink to fall on a blotting paper, the ink immediately spreads. On the other hand, if you imagine a drop of oil placed on top of a glass slide, then you easily can imagine that this drop is not going to spread as easily as you have seen in case of ink on a blotting paper. So, this is because of structural differences though, but this could be a good analogy to explain what is known as wettability. So, in situations where the liquid spreads very easily over the surface, we say that the liquid has very good wettability onto the surface, and the angle subtended will be very small. Now, before that, let's first understand what is this wetting angle that we are talking about, or the contact angle that we are talking about. So, when you imagine a liquid droplet sitting on a solid, you actually can imagine three kinds of interfaces. The solid vapor interfaces, which exists even without the presence of this liquid. The liquid vapor interface, which is between this surrounding atmosphere and the liquid, and the solid liquid interface, which is purely between this droplet and the solid underneath. So, these three tensors actually are the forces will come to a balance, will come to an equilibrium, and that will define or explain what would be the shape that this liquid will take up. If it spreads very easily, then this angle is very low, and we say that wettability is very high. If it does not wet at all, then this angle can be close to 180 degree, and that is when we say that this is non-wetting type. So, in a clean solid, for example, here you see that possibly the liquid can wet very easily, and we have a very shallow angle. On the other hand, if we have a situation where the surface energy is very high, and this because of which the wetting is very poor, and as a result we see a very large contact angle. So, the surface energy essentially quantifies the disruption that happens, disruption of the intermolecular or interatomic bonds onto the surface, and this for a liquid allows us to equate between the surface tension and the surface energy. So, surface tension is force per unit length, and surface energy is energy per unit area. So, they will be numerically equal if we are talking about a liquid. Now, as I was trying to explain, that if you actually cut across a solid, then you create a disruption, and across the section you actually realize that you have unsaturated bonds, and the cumulative effect of these unsaturated bonds give rise to what is known as surface or interfacial energy. And if this sectioning is reversible in nature, then we may say that the energy is, and also we assume that the energy is conserved, then we know exactly that the energy at the surface will be exactly half the energy of the coercive forces existing otherwise among these atoms across the section. So, this is how the surface energy can be defined or related to the energy of cohesion that exists inside the crystal. So, we have already defined that surface is essentially the interface between two identical or dissimilar phases or grains. So, when they are identical, we call them grain boundaries. When they are dissimilar, we call them phase boundary. And for any normal solid, we always will have a solid vapor interface, which also is dissimilar in nature. So, a Gibbs energy, which we know very well is an index of stability of the system, but this is in absolute terms. So, a Gibbs energy of a system which contains not only the bulk, but also the surfaces will have a bulk component, the ideal Gibbs energy, and along with that will be an interfacial component, which is nothing but A times gamma, where A is the surface area per unit volume and gamma is the surface energy. Now, the Gibbs energy, when you differentiate, can also be equated to the force times the incremental increase in area. So, when you actually create a crystal or when you create a surface, then the work that you do actually can be also there will be also a Gibbs energy component associated with the creation of the surface. And so, these kind of mathematical treatments actually allow you to understand that the force that exists onto the surface will be equal to the energy, surface energy, when the variation of surface energy with area is 0. So, this is a typical isotropic situations, but in general the surface energy will have an internal energy associated with it, and the differences coming from the PV terms, the pressure times volume minus the temperature times entropy. So, this will define the overall energy associated with the surface. But in plain terms, we actually must realize that the surface energy or so-called interfacial energy is an important quantity for us to understand the behavior of solids, because this is how it defines. So, for example, in a situation where an incoming droplet does not wet at all, so we now realize that the wetting angle or the contact angle is practically 180 degree, because there is only a point contact between the droplet and the solid underneath. So, in a situation like this, the solid will not get wetted by any incoming, for example, such incoming droplets. Now, this could be a very nice example for the solar panels which we see these days on the rooftops, which harvest solar energy and convert it into electrical energy. This is a welcome situation on such solar panels, because then the panel will not collect dust and other particles and get covered, and eventually that could lead to attenuation in the amount of solar energy that you can harvest. So, in cases where one wants a non-wetting surface or a so-called hydrophobic surface, we will go for a situation whereby the theta, the contact angle, could be as close to 180 degree as possible. On the other hand, we actually may require for certain reactivity, certain transformations or certain other purpose, a situation where the incoming liquid should wet completely, so that the wetting angle is 0 degree. So, for changing the behavior of a surface from completely hydrophilic to completely hydrophobic, one can actually look into the surface morphology, the surface structure, and most importantly the surface energy, so that such characteristics can be obtained. And this is how surface actually also dictates whether a certain reaction can happen easily or otherwise onto a particular surface. And when we talk of situations like a mechanical interaction between two solid surfaces, or mechanical or electrochemical or chemical interactions, then this kind of surface characteristics and behaviors are very, very important. Now, typically, if you look at these cartoons here, you can easily imagine what would it look like an interface between a solid and a liquid. Say, for example, this is the liquid where we have slightly lesser coordination number and wider distance of separation among the species. So, a solid is certainly denser and has a rigid volume. Liquid doesn't have has a fixed volume, but doesn't have a fixed shape, is not rigid, and gaseous substances obviously is much more free to move around. So, obviously, the least dense and distance between the atoms or molecules would be the largest. So, obviously, whenever you have a solid liquid interface or a solid vapor interface, you do see that there is a difference in atomic configurations across. And this is why we actually see all the manifestations of surface related phenomena. Now, talking about the surface phenomena, we realize that every surface carries a certain amount of energy, and that is responsible for certain behavior. So, in order to reduce the surface energy, you can do one of the three possibilities. You can reduce the surface area, because the overall surface energy cumulative term is gamma times A. If you reduce A, or surface area, the overall delta G gamma, or the surface energy associated, is reduced. You can choose certain crystallographic planes which actually have low energy, or in other words densely packed. So, if you expose those crystallographic planes onto the free surface, then the overall energy of the interface of the surface can be lower, or you can actually change the atomic geometry of the surface in order to reduce the surface free energy. So, when we need to tailor the surface, we must remember that we may need to change the structure, or to be more precise, the microstructure of the surface, as a result of which the energy can be reduced or changed. And such change of surface energy is also possible by way of segregation or changing the chemistry in the near surface region. Now, when the crystals grow, then it actually grows in certain, it develops certain contours, certain morphology. And if we divide the entire realm of solids into two major categories, where we have for example metallic crystals and non-metallic crystals. So, for non-metallic crystals, which very well could be ionic crystals, when the crystals grow, we do see such ledge growth mechanism in operation. In other words, since the atomic bonding energy is very high in such ionic crystals, the atoms usually will not be able to come and sit anywhere on top of the existing surface. For example, if you imagine this is a flat terrace or a flat surface, and here is an atom which comes from the vapor phase and jumps across the vapor solid interface and tries to associate itself with this solid surface, then for every such jump you have to incorporate, if you imagine this atom to be a cube, then out of the 8 faces of the cube, only one face which is interfacing with this existing surface is getting annihilated, but in the process you are also exposing 5 new surfaces. So any such jump where a single isolated atom is trying to incorporate itself with an existing solid will be energetically not favorable, because you are creating more number of surface than the number of surfaces you are annihilating in the process. So a single atom coming and getting attached or associated with a flat interface, which is that, for example, of an ionic crystal, is unlikely. On the other hand, if you have such kinks or if you have jogs, then such an atom can actually come and sit in this gap, and when it sits in this gap, then actually you annihilate 1, 2, 3 interfaces on this inner surface for any such atom to come and sit on top. So it's not only 1, 2, 3, also the bottom surface gets annihilated, or you don't need to create a new surface for that. The only new surface that you create is the top surface. So energetically, incorporation of an atom, a single atom, in such a kinked ledge of a growing interface is favorable. Now, this again requires a much longer discussion, but the point I am trying to make is that if you are dealing with metallic surface, then incorporation of an atom onto the growing interface or solid liquid or solid vapor interface is much easier, and as a result a metallic crystal can take any shape. Whereas when you are dealing with ionic crystals with very high bond energy, then the surface morphology will not be random, but will maintain certain preference of orientation and geometry. And this is because the surface energies are vastly different between the metallic and ionic crystals. Finally, I need to tell you that if you take the cross section of any solid, we tend to believe that we, in a naked eye, under our naked eye, we see a shining flat surface. But actually, if you look at, if you zoom on and then if you zoom in and if you look at the various possibilities of atomic distribution across the on the cross sectional plane, then on the top surface you will always see an adsorbed layer of gases or water vapor, and this usually is an oxide or an hydroxide surface layer. The depth or the height of it is hardly a nanometer or even less. Below that will be typically an oxide layer, and this oxide layer is actually is manifested as an oxide. So the top layer is only an adsorbed layer, which essentially just 1 or 2 atomic layers, but below that we have a solid which compositionally is different from the bulk and is an oxide or an hydroxide. Below that we may actually see a highly deformed layer, and there is a large possibility that this layer could be non-crystalline, even if the bulk sitting below is crystalline. And such layer happens or arises because of the various kinds of mechanical processes that we subject the crystal to. For example, while preparing the crystal, we subject it to very heavy amount of grinding and polishing, and that can destroy the three-dimensional periodicity and make such an amorphous layer. But the layer thickness again is very, very small, much less than 100 nanometer. So it could be just a few nanometers. And then we have, of course, a certain amount of deformed layer where we have density of various kinds of defects, but essentially below we have the solid that we generally tend to deal with. So in other words, what I'm trying to say is that when we talk of a big bulk solid, we tend to believe that this bulk is exactly the same throughout. We just saw that the top of the solid, the solid vapor interface, is structurally different and certainly carries a certain amount of energy. And the origin of such differences in structure and energy is better understood when you actually zoom into this kind of a cross-sectional plane and go layer by layer, and then you realize that first 1 or 2 nanometers, then a few tens of nanometers, and then again another tens of nanometers could be very different structurally and compositionally than what you have in the interior of the crystal. So now it's time to summarize. So what did we learn? First, we understood that why do surfaces arise? We have no choice. Whenever you talk of a solid, it has a finite volume, and because of this finite volume, you certainly will have an external surface, and this surface carries certain energy, and hence it is this surface energy which is important for us to know. So we also talked about why are these surfaces important for solids, because they actually explain quite a few phenomena that is commonplace for all these solids. For example, why some of the solids or metals rust, why some of them develop certain chemical layer on top which is different than the bulk, why certain surfaces behave as hydrophobic while some others could be hydrophilic, the so-called hydrophobicity or the lotus effect can come either because of the structural reason or because of the compositional reason, but is easy to explain in terms of the contact angle, which in turn is related to the surface energy. So we classified the interfaces in various forms, and I gave you the basis for such classification. And what is important for us is to know that the surfaces actually differ from one another in terms of can differ from one another in terms of angle of misorientation and the amount of energy or the degree of coherence between the neighbors and so on. Finally, we also realized that the natural shape of a crystal is also very significantly affected by the surface energy, and hence because the missing bonds at the surface could vary from metallic to non-metallic or ionic crystals. And as a result, we always tend to see that ionic crystals manifest themselves with flat interfaces or faceted interfaces, and metallic crystals can take any type of shape we want when we pour, for example, liquid metal into a particular container and then cast a particular product. So with this, we come to an end to this, the fourth lecture of the series, and now onwards we'll have to move on and discuss various surface dependent properties. Thank you very much.